again, a very simple introduction to the whole process. But let's look at the next one in the handout that I gave you guys. And let's see how it works. Now, when it comes to NMR, I always say keep a ruler handy. Keep a ruler with you. Because there are some measurements we have to make. Do you guys have rulers with you?
No.
Okay. Keep a ruler with you. Because you will need it for NMR. Like this one. Is this the next one on your handout?
Yeah,
Cool. Perfect. Perfect. Now let's start from the top. Let's calculate the IHD first. Please, IHD first. The formula is C4H9Br. So what is the IHD for this molecule?
0.
Is it 0 again?
Yeah.
Okay, half of C4. So C4H10 is saturated. C4H9 and Br, you're adding 10.
You're replacing the bromine with a hydrogen.
Exactly. Again, meaning no pi bond, no ring. You guys with me?
Yeah.
Number of signals. So that's TMS, you don't have to count. That's a reference, it's not part of the compound. How many signals? Here is one. It's enlarged there. Sometimes we enlarge it, sometimes we don't, depending on. So this signal, notice it's at around 1. Notice that's around 1. So this signal is enlarged over there. Agreed?
Yeah.
Number 2, right here, is enlarged right there. Number 3, there is another signal right there next to the 2, which is zoomed in right there. And the 4th signal around 4 ppm is enlarged right here. You guys seeing it?
Yeah.
So how many total signals for this compound?
4 signals.
Which means there are 4 types of hydrogens in this molecule that we have to think about. Is everybody with me? So I'm going to just call this A, call this B, C, and D, which means this is A, this is B, C, and D. Okay. Let's look at now integration. This is why we need a ruler. The way our instruments show us the integration is using this curve that you see. And that's what you will be doing in the lab upstairs too, by the way. This curve that you see that's above signal A is giving me the integration for A. This curve that you see ending right there, which is above signal B, is the integration for B. Starting from here, going all the way, which is covering signal C, is the integration for C. And this whole thing is the integration for signal D. So what we need to do is use a ruler and measure the distance between, what I like to do is, okay, draw this line and, so measure the distance between the start of the curve and the end of the curve. So and again, the units don't really matter as long as it's a ratio, so the units don't matter. I have 15 millimeters or 1.5 centimeter, fine. But the critical part is, which is what confuses a lot of people, the signal B is only being covered through there. So this distance is signal B. 1, 2, 3, so about 30 millimeters or 3 centimeters. Signal C does not start from here, guys. Signal C starts where signal C starts, which is, see, this is the start of signal C. So the integration for signal C starts there as well to the end. So let's see how many centimeters that is. 1, 2, 3, 4, so I have 45 centimeters. Excuse me, 45 millimeters, not centimeters. And then let's see what this is again, from the start of the integration curve to the end, it's 1, 2, 4, 45.
You're also saying it's milliliters as well.
Millimeters, I said
Millimeters, not
meters.
liters.
No,
Okay.
millimeters, yes. But you can measure in centimeters, you can measure in inches, doesn't matter because integration is a ratio, so the units will cancel out. Millimeters, yeah. Milliliters would be confusing.
Yeah, I was like, oh no, is this related?
No, that's it. So we are just measuring the distance there. Are we good, everybody, so far? So let's look at, I'm going to start with A. Integration A is to B, is to C, is to D. What is the measurement for A is 15. What's the measurement for B?
30.
And 45 and 45. Am I right? What's the ratio?
1 to 2, 3 to 3.
Perfect. Everybody okay?
Yeah.
What is 1 plus 2 plus 3 plus 3? What is the sum of these numbers?
1 plus 2 is 3 plus 2 is 5 plus 3 is 8.
8?
Oh, 1 plus 2 is 3
Right.
plus 3 is 6 plus 3 is
Does
9.
that match the number of hydrogens in the molecule?
Yep.
So is it reasonable for us to say that signal A is 1 hydrogen, signal 2 is 2 hydrogens, 3 hydrogens, 3 hydrogens? Is that reasonable?
Yes.
Everybody okay so far? Yes? Cool. Now again, 3 hydrogens, what likely is it? What kind of group is it most likely? Sorry.
Methyl.
So we have a methyl, we have a different methyl. 2 methyls that are not identical to each other,
Yep.
right? Because they have different signals. What about 2 hydrogens? And what about 1 hydrogen? A methine. Everybody okay? So those are pieces that we have come up with so far. Are we good? Everybody okay? Now let's look at multiplicity. Let's again start with from A and we'll just go down the list. So let's starting with A, and what are the multiplicities? B, C, and D. So let's look at signal A. It's zoomed in here so you can count better.
6.
Exactly. 1, 2, 3, 4, 5, 6. Do you agree?
Sextet.
So what about B? What is multiplicity for B? Which is called what?
Pentet.
Either a pentet or some people call it a quintet also. Totally fine. What about signal B?
You mean C?
B.
C?
Double. Or did I already say B? Sorry,
Yeah,
C.
we went
Sorry,
over
C.
B already. C.
Doublet. 2.
Doublet.
Agreed? And what's the signal multiplicity for D?
Triplet.
Triplet. Everybody okay? Now we are going to do some critical thinking, some critical analysis here. We have a CH, we have CH2, we have CH3, we have CH3. How do we take those 4 pieces, connect them to each other so we can have a sextet, a pentet, a doublet, and a triplet? Suggestions. Here is where our creativity comes into play. This is the puzzle solving part of the whole process. So we have 4 pieces here, CH, right,
Yep.
with 3 open bonds.
With 3 open slots.
We have CH2 with 2 open and 1 CH3 and another CH3. How do we put these 4 pieces together so we can get a triplet and a doublet and a pentet and a sextet?
Well, 2 CH3 in the sextet? I don't know.
The CH.
If this is a triplet, what should this be connected to? If this is a triplet,
CH2?
do you guys agree? Okay, fine. This is a CH, if that helps to label them right next to each other so we can see. If this is a triplet, does it make sense that it's connected to that?
Yep.
Okay. This is a doublet. So what should this be connected to be a doublet?
The CH.
Now that's a pentet. So let me just bring these together. So we are bringing these 2 together, right? Isn't that what you said?
Yeah.
CH3CH, there are 2 more open spots. We're putting these 2 together, so now we have a CH2, CH3, now we have 2 pieces. how do we now count for the pentat and the sextet? What do we do? And remember, there's a BR also that we have not brought into the picture. The molecule had a BR as well.
Yep.
Any suggestions?
You can put CH2 to the CH.
And
BR.
here you have a Lego piece with two attachment positions. Here you have a Lego piece with one attachment and one attachment. Do you think that it makes sense for us to, okay, here we go. Let's put a BR here. Let's put CH2, CH3 here. Now everybody is happy. You're done. Make sense? Now does this go on the top or bottom? Who cares? We're not showing stereochemistry here. You could have put this, I mean, anyway, it doesn't matter. So you could have just drawn, that's the structure. Everybody's seeing this. So we are gathering clues and then coming up with pieces and then trying to put the pieces together that would make sense based on the spectrum. So one thing that I ask everybody to do when you're dealing with spectra, both IR and NMR for that matter, is assign your signals. So you'll see this question come up too. Oh, figure out the structure and assign the signals. What that basically means is once you say, okay, that's the structure, then which of these hydrogens is D?
One of the pieces.
Which position is D? It's supposed to be a triplet. So do you agree that that is D?
Yep.
What about C? That's C. Which one is B? Integrating for two hydrogens. And this is D. So big
A.
sorry, thank you. So what we are doing is we are telling the reader exactly which signal corresponds to which hydrogen in the structure you came up with. That's called assigning the signals. Make sense, everyone? Questions on this one? Everybody understands the integration part? Okay, let's look at another one. Now here is an example that gave us some IR information as well, along with the proton NMR. In fact, I'll have another worksheet for us to work that combines IR NMR because they all go together. So let's start with IHD first, because again, a logical place to start if the chemical formula is given. So what's the IHD?
C.
Oh, that's O, C8H8O. You must be wondering, what does that say? I apologize for my bad handwriting.
C18H.
C8H8O.
Okay.
So what's the IHD? How do we modify the chemical formula if there's an oxygen? You
Drop oxygen.
add any hydrogens?
No.
Okay, what's the saturated formula for C8?
So,
It's
C18.
yeah.
minus C8H8. What is that? Oops, H8. 5.
IHD is 5.
Hint number 1. Whenever you see IHD equal to 4 or above, whenever you see IHD equal to 4 or higher, think of benzene ring. How many IHDs does benzene ring account for? How many pi bonds in the benzene ring,
3
guys?
pi bonds.
And rings? How many rings?
6.
6 rings? No. Please.
1 ring.
If you
Oh,
think
yeah,
of
yeah.
a benzene ring, how many rings?
1 ring.
And pi bonds?
1 ring and 3 pi bonds.
So what is the IHD of benzene ring alone? One benzene ring IHD equals? Every pi bond is 1 IHD. Every ring is 1 IHD. So 1 IHD, 2, 3, 4. whenever IHD comes out to be 4 or higher, think about, could there be a benzene in this compound? And where is the confirmation in this spectra that will confirm that, yep, you have a benzene, or no, you don't have a benzene? Anybody? Where does benzene hydrogens show up in proton NMR?
Oh,
Right there.
This area.
From 7 to 8, 6.8.
6.5 to, yeah, exactly.
Yeah.
So the point is, I see my brain is doing this. I see IHD 5. Oh, could there be a benzene? Suddenly I look in this direction, I see, oh, yep, absolutely. There are signals there which confirms that this molecule has a benzene ring in it. Everybody okay? Everyone okay? Okay. We'll do more with it as we go forward. Just keep that clue in mind. Okay, let's look at IR and try and see what can we gauge from the IR data given to us in this particular example. So what do we know here? So 3100 centimeter inverse, 2850. So what is this signal suggesting in IR?
3100 is sp2ch.
Absolutely, that means, which makes sense, because if there's benzene ring, there's bound to be sp2 carbon hydrogen bonds, right?
Yeah.
What is 2850 suggesting?
SP3.
sp3 what?
The CH.
sp3 carbon hydrogen bond. So okay, there are also some sp3 carbons with hydrogens on them that we have to think about. What about this? I mean, is there a significance to this set of data? It's doublet between 2700, 2800 and 2800, 2900. Is there a significance to this data? Aldehyde what?
Aldehyde OH.
There's no OH in aldehyde.
Oh, aldehyde.
SP2.
Aldehyde what? CH.
Aldehyde.
The CH bond in an aldehyde group, this bond is being shown by the doublet. So what about this bond then? What about the CO double bond of the aldehyde? Right there. Make sense? Everybody with me? And of course that might be carbon-carbon double bonds, which of course makes sense, because if you have benzene, you also have to have carbon-carbon double bonds and so on and so forth. Are you guys with me so far?
Yep.
So what clues do we already have, even just without even looking at any of the signals? What clues do we already have? We know that first of all, keep in mind C8H8O is the formula, IHD is 4, not 4, excuse me, 5 that you calculated. We've already figured out that, yep, there's some kind of a benzene ring in there, right? What else have we figured out?
Aldehyde.
There's an aldehyde group in there. How many IHDs gone? 4 here, 1 right there, 5 IHDs taken into account. Are you all seeing that?
Yes.
Everybody seeing that?
Mhm.
So these accounted for.
Okay.
Now let's see, okay, how many carbons is this? How many carbons here?
8.
Ooh, harder.
Oh,
How many
1
carbons
carbon.
here? So how many total have we accounted for so far? 7. We still have 1 more to think about. Keep that in mind, right? Everybody? Hydrogens is a little bit tricky because it depends on what's the substitution pattern and blah, blah, blah. We'll come back to it. So see how we are gathering tools as we get to clues, and then we'll put those clues together. Any questions so far? Okay, let's look at NMR now, proton NMR spectrum. We've taken whatever we could from IR. Let's now focus on proton NMR. How many signals?
3 signals.
3 signals? Where? What? Let's label them just so that we can all make sure we're talking about the same thing.
P2 3.6.
Do you agree this labeled as B?
Yeah.
It's been expanded here. Notice the chemical shift state.
Oh.
So this is B expanded,
Yes.
zoomed in. So you can look at it a little closer. We good?
Yeah.
Then what else? CDE. So there are basically a bunch of signals there. So 3 of them, right? C and D and E, they are kind of together. Okay. 1 more. And that, please notice, is, it's kinda here, but they cut it off, so A was showing here, so they took it out and put it there so we can see it. Are we good? And please notice, this is the expanded A. The A has been expanded, so we can take a look at it a little bit closer. Are we all good? Okay, now let's calculate the IHDs. So there are, so what's the total number of signals again? 1, 2, 3, 4, 5.
Oh, 5 signals.
5 total, right? Okay, 5 types of hydrogens first. I think so. Okay, let's do integration now. Where's my ruler? I lost it. Ugh. See, this is why I don't like clutter. So I can't find it. It's right there. Okay. So for signal A, I'm going to measure this distance, right?
Yep.
So 10, 13-ish. By the way, we should always take that with a pinch of salt because sometimes we have to adjust it. Maybe it's not 13, maybe it was just 10, but it measured 13. So we have to be a little flexible with the integration part. Now, for signal C, D, and E, because they are so close to, because these are so close to each other, there's no way we can separate those. Do you guys agree? So I'm going to take those together through that point. And then this part I'm going to measure separately. Is that okay with you? Because, I mean, it's not possible to measure them separately if they are overlapping each other. How do we do that? So let's see. 1, 2, 3, 4, about 41, 42, something like that. Let's again keep that always with a little bit flexibility in there. And then for this signal right here, this one right there, I'm going to measure from here. So 1, 2, 3, so about 30-ish. And then we have signal B. Let's see. How much is that? 1, 2, 25, 27, maybe 30. So again, we are always being a little flexible with the integration measurements. 30, 13, 42. Okay, so can I, again, please, I'm thinking aloud here. Thinking aloud so you can hear what I'm thinking. Okay, being a little flexible with my integration numbers. Maybe it's not 42, maybe it's 45. And which means maybe that's 15, because then it makes sense. If the integration is 15 is to 45 is to 30 is to 30,
1, 3, 2, 2.
makes sense,
Yeah.
right? If you had 13 and 42, it kind of doesn't make sense. So we are being a little flexible there, right? So what is the ratio? Yeah, somebody started to say it. Could you please say it again?
1, 3, 2, 2.
Exactly.
1, 3, 2, 2.
1 to 3 to 2 to 2. What is 1 plus 3 plus 2 plus 2?
1 plus 3 is 4 plus 2 is 6 plus 2 is 8.
Is that the number of total hydrogens in the molecule?
Yep.
Yes, Tash?
What about the two groups that are connected together?
Good. We'll get to that. Hold on to that thought because, yeah, I mean, right here, right? We took 2 of them together. So what does that mean? Hold on to that thought. So at least for now, what we have, can we say this is 1 hydrogen, this is 3 hydrogen, 2 hydrogens, and 2 hydrogens as being accounted for? Agreed? And does that add up to 8 hydrogens that the molecule actually has, C8H8O?
Yep.
Perfect. Okay, so we've taken care of that. Now let's look at multiplicity really closely. I need to erase this. Let's start with the leftmost signal. Now, what's the multiplicity for that? Has been zoomed on shown.
Triple.
What are they labeling it as? Is that A? Is that, I can't see.
A is between 9.65 and
So let's start
9.75.
with A. What is the multiplicity? Triplet, right?
Triplet.
Because please notice that signal around 9.7 is being zoomed here. Do You see 1, 2, 3? Because sometimes when the split are too close, you can't see it. So you can highlight that area and you can zoom it up. So you can see it better. Everybody seeing that? Okay, let's go to, where is B?
B is to
here.
the right.
I want to go in order. Can we just go in order?
Yeah.
C,
Okay.
D, E, and then I'll do B. Okay, what about C and D and E? Can you tell? It's pretty complex, isn't it? It's like bunch of different lines split, very hard to tell. So don't, because it's very complex. We're not able to very clearly make out what the multiplicities of these are. And then what about B? What is that? That's a doublet. Okay. Now taking these into account, before I go any further, can you focus on signals that are C, D, and E? These signals right here. What kind of hydrogens show up right there? Benzene hydrogens, isn't that right?
Yeah.
Benzene hydrogens, and we expect a benzene. So these belong to benzene. But how many total hydrogens are these three signals accounting for?
Which makes sense.
Right? If there are 5 hydrogens on the benzene, how many other substituents does the benzene ring have? Sorry?
1.
A monosubstituted benzene. There's only one more available place for benzene to have something else on because the others are 5 hydrogens. Is everybody noticing that? Everybody okay? Yes? Good? Okay. Now this is 2 hydrogens. This is 1 hydrogen. This is 2 hydrogens. That's a doublet. This is a triplet. Is it okay therefore for us to combine them? Those are connected to each other?
Sure.
Right?
Yeah.
Because this is a triplet because of the 2 hydrogens. This is a doublet because of the 1 hydrogen. Would that make sense? Everybody okay? So what else do I have? I have a CH connected to a CH2. Isn't that right? Okay. We all look good so far?
Yeah.
What is so special about that chemical shift value?